right. So today, tonight, whenever, we are doing reactions. So, stoichiometry, types of reactions, balancing equations, how do you read a chemical reaction, etc. Before we start, one quick thing from yesterday that I forgot to review. A percent comp of a hydrated compound. So that means it's a compound that's been hydrated with water. So you'll often see it like MgSO4.5H2Os. So that's magnesium sulfate pentahydrate. So it's like magnesium sulfate, but it's been hydrated with a certain amount of water. And if you need to find, there's usually two ways they'll throw this at you. If you need to find the percent composition of, let's say, the water in this compound, you also need to make sure you include the MgSO4. So MgSO4 should have a weight of 148 grams per mole. So if I add up Mg, the 4 oxygens, you should get about 148 grams per mole, I think, unless I'm adding it wrong. No, that's 120. Did that in my head a little too quick. 120 grams per mole. You also need to make sure you include the 5 waters in your total weight. So 5 times the weight of water of 18 will give you 90. So if you're looking for the percent composition of water in this hydrated compound, it would be 90 divided by 120 plus 90. So the part divided by the whole times 100. And that should give you about 43%. So that's one way they can present you a percent composition problem of a hydrate. They could also do like a before and after scenario. So a hydrated compound weighs 10 grams. After you heat it, it weighs 8 grams. After you heat it again, just to confirm your results, it still weighs 8 grams. So if you are hydrated, that means with water, you weigh 10 grams. After you've heated it, we call this an anhydrite portion because when you heat, H2O evaporates. So this tells you how much water was in the compound. And since it lost 2 grams after heating, we can assume that those 2 grams that it lost was water. It had 10 grams total at the 2 divided by 10 times 100 is 20%. So those are the two ways they'll present it to you. All right. How do we read a chemical reaction? What does everything mean in a chemical reaction? So let's say you were forming ammonia. You read this from left to right. Left to right. And the way you would read it is the green parts are called your reactants. So the green part in this reaction is your reactant. The arrow means make. And let's not make this like equilibrium. And the red part are your products. So the reactants make products. What goes in makes what comes out. You read these from left to right. Into out. Into out. Reactants make products. I'm going to rewrite this reaction again. When you look at this reaction, these big numbers are coefficients, which is the same as moles. So in this reaction, we have 1 mole of N2 reacts with 3 moles of H2 to make 2 moles of NH3. Okay? So the big numbers here mean moles. And those are called coefficients. When you see a chemical reaction, so chemical reactions will always be making or breaking bonds, but you will conserve mass, you'll conserve matter, you'll conserve energy, and you'll conserve charge. And all that means is what goes into a chemical reaction must be the same types of atoms that come out of a chemical reaction. They're not going to be the same thing. So N2 is not the same as ammonia. So when you see this reaction occur, these are all different things, so they're different substances. They are different of each substance. But if we look at the left side and look at the right side, the left side has 1 N2, which is the same as saying we have 2 N's. If we look at the left side, we have 3 H2. So since we have 3 H2, that means we have 6 H's. The right side has 2 NH3, which is 2 N's and 6 H's. So what goes in is the same amount of atoms, the same types of atoms, which have the same mass. So that's all conserved. That all remains the same. However, they form something different. They're all different substances with different properties reacting, in this case making a bond, to form something with that's a different substance with different properties. So when you look at reactions and you think about making and breaking bonds, you're going to think barf. Breaking a bond absorbs energy, while releasing energy forms a bond. So, if we look at O2 breaking down into 2 O's, this bond here is being broken into 2 separate O's. So this absorbs energy. Versus if we look at something in reverse, let's say the 2 F's react to form F2. Well, here we made a bond. Those 2 F's combined to form F2. So this is releasing energy. So if you form a bond, you release energy. If you break a bond, you absorb energy. So those are some intro basics to reading a chemical reaction. What do you do if the mass is not the same going in and coming out? That's when you need to balance. So I'll start with an easy one. H2 plus O2 make water. You need to conserve mass. You need to conserve your atoms here. So the same amount of atoms that go in have to be the same amount of atoms that pop out. So if I look at this, the way I balance equations is I draw a line down the arrow, and I just write, what are my atoms in this reaction? Well, I have H's, and I have O's. I have H's, and I have O's. Count. How many atoms do you have? 2 H's here, 2 O's here, 2 H's here, but only 1 O there. So, those reactions, this reaction I should say, is not balanced. I have 2 O's going in, 1 O coming out. 2 go in, 1 pops out. That's not the same. We need to get those to be equal to each other. So I could very simply take this O and don't add, but multiply it by 2, and now I have 2 O's. So I need to come up and change my coefficient here to a 2. But when you put that 2 in front, make sure you change every atom in the compound. So now I don't have 2 hydrogens anymore. I have 2 times 2, which is 4. Which means now I have to go back and fix this hydrogen here, because I said initially only 2 of those were going in. So if I multiply this one times 2, now everything is the same. I put my 2 in front here. You can leave that blank. If it's blank, we assume it's 1 mole of that oxygen. But you can write the 1 in if it makes you happy. Do whatever makes you happy. Does not matter to us as teachers. We understand that if you leave it blank, we know it means 1. All right, let's balance another equation. Let's do CO2 plus H2O make C6H12O6 plus O2. All right, I'm going to draw my line. C, O, H. These are all the atoms I have in this chemical reaction here. And they're on both sides. Now, typically, the advice that I give is do oxygens and hydrogens last. It's usually a good piece of advice. Do oxygens and hydrogens last. Might not always work, but most of the time, that's what you want to do. So let's count here. I got 1 carbon on this side, and I have 6 carbons over here. I have, oxygen's next. 2 plus 1 oxygen, that's 3 over here. 6 plus 2, 8 over there. Now you see right now, before I do the hydrogens, why you do the oxygens last. Trying to figure out what to do with a 3 and an 8. How do I get that to be even? That can be kind of hard. That might take a while. I mean, you can multiply the 3 times 8 to make it 24. Multiply the 8 times 3 and make it 24. But maybe we won't have to do that. Maybe this will work itself out. So always save the oxygens and hydrogens for last. Especially save for last the ones that you have multiple appearances of on both sides. And what I mean by that is oxygen pops up twice over here and twice over there. And when that happens, you typically want to save that one for last. Hydrogens, I have 2 over here and 12 over there. So just looking at the carbons and the hydrogens, I'm going to do those first because I think it's the oxygens will work itself out. So the carbons are pretty easy to see what to do up front. If I multiply this by 6, now they're both 6. I'm going to put a 6 there in front of the carbon. Now I have to change my oxygens because now I have 6 times 2 which is 12, plus the 1 here, which is 13. Oh, I didn't have to erase that. That's okay. 13. Yeah, now again, you look at those oxygens, 13 and 8, that's not pretty. Let's do the hydrogens first. If I multiply these hydrogens times 6, you get 12. 12, 12. So, I'm going to put a 6 in front of those hydrogens, and I have to go back, and now I have to fix my oxygens again. So, 6 times 2 is 12, plus 6 times 1, which is 6, is 18. So, over here, I have 6 oxygens from this guy, plus the 2 oxygens from that guy. I need to get that to be 18 somehow. So initially you might think nothing times 8 will get me to 18. However, if I keep this one the same, what can I multiply this oxygen to add it to that 6 to make it 18? You might be saying to yourself, wait, 12 plus 6 is 18. So if I put a 6 right here, now it's 6 times 2, which is 12. 6 plus 12 is 18. Worked itself out. Put a 1 there if you choose. On the Regents review on my website, there will be a lot of balancing equation problems that I will upload. You can see over the years how hard or how easy they may be. Some years, I'll be honest, they're very simple balancing. Other years, a bit of a pain in the butt. I don't know if you'll see one this hard, like the one we just did, but you could. You could. So it really depends on the year how gracious they're going to be. All right, other things with chemical reactions. Mass is conserved. So if we take the water equation we just had, we have to conserve our matter, which we do here, and we want to conserve what goes in is the same as what goes out. So that means the mass in has to equal the mass out. What goes in needs to be the same as what goes out. What comes out might be a different substance with different properties, but the mass and the types of atoms should be the same. So, if the reaction says you have 10 grams of H2 react with 15 grams of oxygen, well, that's a total of 25 grams. So theoretically, if this goes to completion and we ignore like limiting reactants and all that fun stuff, we better see 25 grams of H2O pop out. We can't just lose that mass. And they like to ask this question a lot in a few different ways. So, another way I've seen it in the past is I'm going to make this ammonia equation again because it's easy for me to remember. It'll say you have 100 grams of ammonia be produced. If 40 grams of N2 were reacted, how many grams of H2 were reacted? Well, at a very simplistic level, mass needs to be conserved. So if 100 grams popped out and 40 went in, the other 60 grams better be from the hydrogen. Now, what about the types of reactions? What are they? So, first, there is synthesis. So synthesis is when you take 2 or more atoms and combine them together to make one bigger compound. So, the water reaction would be a classic example of synthesis. 2 things become one bigger thing. Decomposition. Decomposition is when you take one bigger thing and split it into 2 smaller parts. So that would be like the opposite of what you see above. decomposition. Single replacement. Single replacement, oh, that's not how you spell replacement. Single replacement will always involve an atom by itself reacting with a compound. So, for example, you might have a single lonely Mg reacting with, let's say, hydrochloric acid. So what happens in a single replacement is you have a single switch. You take the atom that's alone and you switch it so that Mg is positive and H is positive in these compounds. You just take the two positive atoms, or if the two in common are negative atoms, and you switch them with each other. Check your charges. Magnesium is +2, and chlorine over here is -1. Since chlorine's -1 and Mg is +2, you got to crisscross those numbers going down. So that 2 comes down here, and that 1 goes down there. You don't have to put that 1 there if you don't want to. It's implied that it would be 1. Why did I make the H diatomic? Why are there 2 of them? So in a chemical reaction, when you form, and this would be in the gaseous phase typically, Brinkelhoff, these 7 elements will always be diatomic, meaning 2 of them. Not in aqueous though. This is not AQ. So don't do it if you see AQ. It's only when they are produced in a chemical reaction, and typically these will be produced as gases. Not necessarily, but typically. Other teachers will do Hober-Finkel, Hoff-Brinkel. Dilo does a different one. Mr. DiLorenzo does one, and I always forget what he does, but it's different. Or is it Miss Bell? I learned it as Brinkelhoff. So whatever mnemonic your teacher gave you, you can just use that. Not mnemonic. Is it technically a mnemonic? I don't really know. Now, there's a lot of applications of these reactions that I'll get to in later videos. Like, we'll talk a lot about single replacement again when we're in redox. We'll talk a lot about double replacement again when we do solutions. I just don't want to take up too much time here. If we have a lot of time, like if I notice we get through a lot of more material than I think, then maybe we'll come back to it. But I really want to save some time for stoich. Did I put that on the agenda? No, I just said reactions. I want to leave some time for stoichiometry. And you're like, what? You'll see what I mean. So double replacement involves 2 compounds. So technically, acid-base neutralization is a type of double replacement. So when you react 2 compounds, like these acids and bases, the 2 positively charged species or atoms will switch with each other. We'll get NaCl and HOH. So this is acid-base neutralization. So you form salt and water. So if you're identifying a double replacement reaction, you need to see the double switch. Na and H both trade with each other, and both Na and H bonded to somebody new. They like to ask prediction questions with these. So sometimes you might see something like SO4 or let's do MgOH2 plus HCl again. And it'll be like blank plus H2O. And this is not balanced at the moment, but that's okay. Did I balance the single replacement one? I didn't, Mr. G. Always balance your equations. There should be a 2 there. Okay, so how do you predict that blank? Well, think about what we said before. Everything's conserved. What goes in needs to be what pops out. The O's and the H's already popped out in H2O. Not the exact amounts, because it would need to be balanced, but they're there. They have been accounted for. What's missing? First, you can say to yourself, Mr. G, can't I just switch the Mg and the H, and that's how you got water, and then the magnesium will be at the chlorine? And I would say yes, that would be a great idea. But what's another way to figure it out? If you look on the left side and you look on the right side, right now there's 2 key components that were going in that didn't pop out. Well, those 2 things were Mg and Cl. So make sure we account for those. Check your charges. They have different charges. They don't cancel each other out. There's a 2 and a 1. So crisscross and bring them down. I brought the 2 to Cl. A lot of times this will already be balanced for you and you just need to fill in the blank. So just make sure you go back and you balance your equation here. And that's it. That's double replacement. The last one that I always included with this unit, that you don't have to, because some people will do it with organic, we'll bring it up again, and that's combustion. And that is when you take any hydrocarbon, so any CH compound, plus oxygen, will always make the same 2 products every single time. Carbon dioxide and water. I don't know why I started using formulas on the right side, but I went with it. So any hydrocarbon plus O2 makes CO2 and H2O. Doesn't matter what order you add these in. No. You could do O2 plus C2H4 make H2O plus CO2. Or you can do O2 plus C2H4 make CO2 plus H2O. It's like that additive property in math. 1 plus 2 is the same as 2 plus 1. 3 plus 7 is the same as 7 plus 3. So that really doesn't matter. You got to balance this equation because this isn't balanced. Is that it? 2, 4, 2, 4. Yep. So make sure all of these are balanced, balance, balance. All right, so that's combustion. A hydrocarbon will react with oxygen and always produce carbon dioxide and water. All right, stoic. Stoic will not get any more complicated than what I'm about to show you. I'm going to do the lovely ammonia equation again. When you read this reaction, the mole ratios of these compounds are 1 to 3 to 2. For every 1 nitrogen, 3 hydrogens react and form 2 ammonias. That ratio will always stand true regardless of how it is changed and manipulated. So, let's say there's a question that's like, what if 4 moles of NH3 are made? How would this change the amount of hydrogens and nitrogens that reacted? How much nitrogens and hydrogens must have reacted to create those 4 moles of ammonia? Well, you can just set up a proportion. So, for every 3 moles of H2 from my balanced equation, I produced 2 moles of NH3. If 4 moles were produced in the reaction that you performed, how many moles of H2 must have been reacted? Cross multiply. 12 equals 2x. Divide both sides by 2, and x would be 6 moles of H2. The same thing, the same way to solve this is also true for N2. In my balanced equation, 1 mole of N2 produced 2 moles of NH3. If 4 moles were produced in your chemical reaction, how much N2 must have reacted? Cross multiply and divide. 4 equals 2x. Divide by 2, and x would be 2 moles of N2. Other ways you might see this problem. Let's use the same reaction. Sometimes they like to change 2 things at once. So what if 1.5 moles of, let's do 0.5 moles of N2 produced 1 mole of NH3? How many moles of H2 were reacted? And in this scenario, I think it's easiest if you just pick one of them and set up your proportion with one of them. So I'll show you with both, but all you have to do is pick one. So let's say you picked N2. So in my balanced equation, 1 mole of N2 is reacting with 3 moles of hydrogen. If you had 0.5 moles of N2 instead, how many moles of hydrogen would react? Cross multiply and divide, you get x is equal to 1.5. You could do the same thing with NH3. From my balanced equation, 3 H2s always produced 2 NH3s. How many H2s are reacting if I now have produced only 1 NH3? Cross multiply and divide. 3 equals 2x. X again is equal to 1.5 moles of H2. That is pretty much the extent of the stoichiometry that will appear on the Regents. You will not need to do what I just did and determine the mass, or determine the molecules, or determine the liters. You will not be given a mass and asked to get another mass. It will always be going from moles to moles. And if you just use the balanced equation, set up a proportion, cross multiply and divide, you're pretty much guaranteed to get it right unless you make a silly algebra mistake. And it happens, but take your time. All right, let's see. What else is there to get through as I hide from the camera? Where'd he go? All right. That it? If that's it, we might as well do table J. That? Really? I feel like I'm missing something. I guess since I did moles yesterday, that covered a lot of it. Moles tends to be a pain. Just looking over my outline here. Yeah, I guess that's it. Let's talk about table J. We got time. And then I'm out of here. All right, so single replacement reactions can be spontaneous. And if you see this question that's like, is this reaction spontaneous? You need to use table J. Or sometimes single replacements, they'll ask a question like, will this occur spontaneously? So it's usually almost always framed around this idea of spontaneous. Will this occur spontaneously? Is this reaction spontaneous? Which one of these reactions is spontaneous? Etc. So you need to use table J. So if we do the example from before, we did Mg plus HCl made MgCl2 plus H2. Sprinkle that off. Put a 2 in front. Put a 2 in front to balance. Was this reaction spontaneous? Did I just make it up? Does this reaction occur spontaneously? How do you know? You need to use table J. So, if I look at table J, I'm going to find the two things that are switching with each other. And those are Mg and H. Mg, H. Mg is more active than H. If the single element, the single atom, the one that's alone, the one that is not in the compound, is higher than the other atom in the compound, we would say these two would react spontaneously. If you take HCl, put it in a beaker, and throw a little strip of magnesium in there, you're going to do nothing. The only thing you did was allow these two things to come into contact with each other, and boom, it's going to react. So, if you're using table J, and table J has multiple uses a lot in redox, oxidation reduction, the atom that's higher than the other will cause a reaction to occur spontaneously, which means it will just occur. You will not have to input energy. The only thing you have to do is bring them into contact with each other. And as soon as you bring them into contact with each other, they go. So that's table J. The higher you are in table J relative to the other atom, the more likely they will react spontaneously, because the higher atom is more chemically active than the lower atom. I guess this is one of those videos I thought was going to take a lot longer because balancing equations always takes a while. And then you realize that once you've kind of learned how to balance equations, they get a bit easier. Because we spend so much time in class practicing these things. So, I think that's it. I can't really think of anything else I want to do right now. We did balancing equations. We did the 5 types of chemical reactions. The big one is just remembering this idea of conservation. Conservation is big. The left makes and reacts to make the right side. The reactants make products. The two things on this left side of the arrow are going in, and the things on the right side of the arrow are going out. The coefficients are moles. Chemical reactions, remember BARF. Breaking absorbs. Breaking a bond, like breaking that O2 bond, is absorbing energy, while forming that F bond is releasing energy. Remember that all of these things have different structures. And when you have a different structure, you have a different property, and they're different. Different structures have different properties. So that's a question they like to ask a lot. So let's end on that note. If you were comparing O2 versus O3, or diamond, which is a carbon compound, versus graphite, which is a carbon compound. These are the two they pick the most. Yes, I get it. They both contain oxygen in the first one. Let's make this A. Yes, I get it. A, both contain oxygen. And B, both contain carbon. But a diamond, I hope this is obvious, a diamond is not the same as graphite. It's just not. If I go take my wife's engagement ring and take the diamond out of it and put some graphite in there instead, she's not going to be too happy with me. She'll probably be upset about that. So, these have different structures. As soon as you form a different formula, they're going to have different structures, which means they're going to have different properties. And the same is true for organic. So when we get to the organic review video, you've done isomers with organic. You can have butane look like this, and butane look like this. And yes, these are both C4H10. And I get that. They're both C4H10. So their formula is the same. But you know what's different? Their structure is different. And when you have you're going to have different properties. Structure determines function. I am very hopeful that your biology teachers made that very clear. Structure determines function. That is a huge principle of biology. So even though these are both C4H10, even though these are both carbon compounds, even though that one oxygen is O2 and that other one is O3, it's just one little teeny extra oxygen. They have different structures, which means they have different properties. They have different structures, which means they have different properties. O2 is what you breathe. O3 is the ozone layer. Totally different things. Different structures, different properties. When a chemical reaction occurs, you form something like water here. Where's synthesis? Something that's easier to read here. Combustion, double replacement. So you formed water here. And yeah, that water contains hydrogen. And yeah, that water contains oxygen. But you know what water is? Essential to living organisms. Most of them. Pretty much everything needs water to survive. Hydrogen's an explosive gas. Oxygen is explosive gas. Water, not explosive at all. Necessary for life. Even oxygen. Yeah, oxygen is necessary for us, but there's plenty of anaerobic bacteria that are like, I don't need that. Different things have different structures, have different properties. Chemistry is all about taking stuff, making and breaking bonds, and when you make and break bonds that's new,